My name is Mike Garybill. I live in Charleston and have been a member of this community for nearly 50 years. And the estuary has been a particular area of personal and professional interest. So today, my role, I've been asked to speak to what the proposed PCIP what changes it will bring to the estuary and the ocean. So I'm going to describe what we know so far about the scope and scale of the proposed alterations to the estuary and the ocean. I'm going to identify how sediments and water in the estuary and in the ocean will respond to the proposed alterations. And then I'm going to place the PCIP's proposed alterations to the estuary and the ocean into a historic context. What I won't do, what this presentation doesn't do, is address the economic viability of the project or its costs and benefits, or any of the potential ecological or social implications, or any other implications for estuary or ocean values like recreation, commercial fishing and crabbing, air quality, etc. So part one, scope and scale of the proposed alterations. As Jan has pointed out, there is a lot of information available about this aspect, the dredging and filling activities, because that information has been since 2007 has been being provided to the Army Corps of Engineers associated with the port's proposal to deepen and widen the Federal Navigation Channel. The aspects that involve dredging are, as Jan pointed out, there's going to be a marine terminal on the North Spit. The main channel is to be deepened to 45 feet and 450 feet wide. The ocean entrance has to be dredged deeper and wider than that because of the waves that you encounter over the bar. The curves need to be dredged wider than that because the ships need more room to maneuver. And as Jan pointed out, there are two. All right, so now we've got two turning basins, and the estimated cost for the dredging work that's associated with the PCIP is $550 million. Well, one might ask, Coos Bay already gets really big ships. Why propose a bigger channel? And I think Jan has already alluded to the fact that the terminal is being designed to handle 2 million TEUs a year, and they'll be carried on 3 ships a week designed to carry 13,000 containers on each one. Now, those are big ships. I'll show you some big ships and compare them to that, but I want to point out that they're no longer the biggest ships. There's quite a number of new vessels being built. In fact, more new vessels being built are bigger than 13,000 TEUs that we're proposing to have for the PCIP. So the Coos Bay woodchip ship is 650 feet long. A Neo-Panamax Generation 3, which is the design vessel for this thing, is nearly twice as long as the chip ships in Coos Bay. They have a considerably deeper draft as well. That's a big ship. It's hard for me to understand how much bigger it is because I think of the chip ships as big ships. So I thought, well, what about another big ship? How about a nuclear-powered aircraft carrier? And so the U.S. government Navy has a fleet of nuclear-powered aircraft carriers. This is one of the more recent ones. It's the George H.W. Bush. And you can see that the proposed PCIP container vessels are 100 feet longer than a nuclear aircraft carrier. They're narrower because these are post-Panamax and they need to be able to fit in through the Panama Canal. And they actually have a deeper draft than an aircraft carrier. That upper turning basin at River Mile 8 is being designed, as you read the documents, for a vessel called a Cape-size bulker. And these are big bulk container vessels that are too big to go through any of the canals. So they are called Cape-size because they have to transit around the Cape of Good Hope and the Cape Horn. They're about 900 to 1,000 feet long. And they have deeper drafts because they're designed to carry materials like iron ore, really heavy, bulky material. So here's how a Cape-size bulker, that is the proposed design for the turning basin up by the Roseburg Chip Terminal compares to one of our Coos Bay wood chip ships. And it's 300 feet longer, and it has a much deeper draft, 25 feet more draft. So now we know we have bigger ships and we need a bigger channel. How much bigger does the channel need to be to handle ships that are between 300 and 500 feet longer? So this is a little stripy diagram that is surveys that the port commissioned, 186 surveys. A boat goes out with the sonar and makes a map of the depth of the water as it goes back and forth across the channel. So we have 186 sections of the bay that we can see what the bottom looks like and what shape it is. Once you have that shape, you can turn that into a computer model and simulate that shape, but you can also then simulate a deeper, wider channel that has different specifications. And you can also, the Port of Coos Bay has enlisted the port pilots to go back to this East Coast simulator and run a variety of different vessels through a variety of different channel configurations. And the end result of these studies has come up with what's called the preferred alteration. So here's what a cartoon picture of one of those cross sections might look like. The water level in the bay goes up and down at high tide and low tide. And there's, because you want a ship to not run aground, the depth of these navigation channels is measured below the average of the low tides. So in our case, the current navigation channel is 37 feet below low tide, and it's 300 feet wide. So what's being proposed is to excavate more of the channel bottom, the area shown in orange here, and that will create a deeper channel and a wider channel that's 45 feet and 450 feet. You'll note that the cross-sectional area of the channel, of the expanded channel, is roughly twice the size of the existing channel. One of the things that we learned the last time that we expanded the navigation channel from 35 feet to 37 feet is there's rock that underlies the sediments in the estuary. And it's very important to understand where the rock is and how much rock will be involved, because it's far more costly to dredge bedrock than it is to dredge sand. There's different methods required. So for cost estimates and volume estimates, these studies were important. The reddish colored areas are the areas where the rock is either exposed or just covered with a thinner layer of sand. The blue or greener areas are areas where the sand very deeply covers the rock. So in order to dredge the two turning basins and deepen and widen the channel as configured, about a third of the material is going to be bedrock, 6 million cubic yards, and about 2/3 of the initial construction will be sand material that can be dredged using conventional methods. How much is a cubic yard? Well, it's a big scoop from a big backhoe. It's 1 yard, 3 feet by 3 feet by 3 feet. It's a measure of volume. The port's studies estimate that there will be 32,700,000 cubic yards. So that would probably wear that backhoe out in the process. That's such a big volume, I had a hard time trying to understand how much that is. 32,700,000 cubic yards is enough to fill Autzen Stadium to the brim 7.5 times. If you put it on a train, you could load train cars full of sediment, and that train would start in Coos Bay and would stretch to Vancouver, Washington. Where are you going to put all this material? In order to dispose of this material, the plan is to dispose of it in the ocean, and 2 new dredged material disposal sites are being proposed. One off of Shore Acres in Sunset Bay, and the other one along the North Spit. The area that's involved is about the size of the city of North Bend. So what will happen after you remove those sediments? Well, I've listed 7 items here of things that will change in the estuary and the ocean. I only have time to highlight a few of them, And I'll start with sediments, but I'll talk about a little bit about water, as well as perhaps one or two slides for living conditions. You will recall that little cartoon I showed you, the navigation channel. Our existing navigation channel is the orange box in the middle, and you can see the blue shaded area is the bottom. The proposal is to deepen and widen the channel, so that will mean that's the red box, a deeper and wider channel. And it means that if any of you have ever dug a hole in the sand at the beach, you know that you dig, but the sand fills in from the side. The light shaded blue area is the area that is outside of the navigation channel, is the sediments that's expected to move in and fill in that channel from this process called side slope equilibration, which is what we've all experienced if you've dug a hole in the sand at the beach. Side slope equilibration has been studied by the Port of Coos Bay, and the equilibration areas in total, the area outside of the channel that will move into the channel in response to the dredging is an area about 350 acres. And the brown and red shaded areas show where they are. I'll offer an example up in the upper portion of the bay at that turning basin. There's about 12 million cubic yards of material expected to move in to the channel after the channel has been dredged through a process called side slope equilibration. That volume of material that will move into the channel is comparable to the amount of sand that will actually be dredged out of the channel to start with. It will take some time for that side slope material to move into the channel, which means it will need to be dredged on a regular basis, on an accelerated basis in the first several years until the side slopes equilibrate. And here the equilibration material costs are shown to be about $11 million, starting costly in the first year and diminishing as the volume diminishes as the slopes equilibrate. So let's take a look up there at River Mile 8 at that Roseburg chip terminal. This is the peach colored area is the actual footprint of the turning basin for those Cape-size vessels. The light green shaded area adjoining that footprint of the turning basin is the portion of the bay bottom that will be mobilized and move into that area to be dredged away. So let's look at the deep red line. Let's stand at the railroad bridge and look downstream. So the next image I'll show you is a cross section that will have the chip terminal on the right, and the airport runway would be over toward the left up there in North Bend. Here's a cross-sectional area from one of the reports. You can see that in that section of the bay by the chip terminal, the channel is well dredged. That's the dotted line. And the area to the right of the channel over by the chip terminal is also dredged because Roseburg maintains that because that's where the chip ships park. Off to the left is the turning basin. The solid color is the actual size that the turning basin is proposed to be. But that blue hatched area is the portion of the bay outside of where the footprint of the turning basin is that will be impacted by the construction of the turning basin. If we move down the bay, we get a different story. This is the turning basin that's at the proposed terminal. Yellow dashed line is where the ships will tie, the container ships are proposed to tie up. We've got the hollering place on the lower right portion of the screen. You can see the T-dock highlighted and the old anadromous fish hatchery facility showcased there. I'll show you another cross-section looking downstream of what's going on here at the hollering place. This is the existing conditions. The channel is well dredged. The slopes have equilibrated. The gray shaded area is the bottom. The north spit is on the right, and you can see the wooden pilings that are in the docks at the hollering place on the left. What's proposed is to create a turning basin. The brown shaded area is the area that's to be dredged and the material that's to be removed. Jan mentioned that 50-foot deep pocket berth, so ships don't sit on the bottom at low tide. That's that pocket berth shown here. Well, the big question then is what material? Remember those rock graphs I showed you? What material is to be discovered? Well, in this case, the footprint of the turning basin for the container ships in Empire at the hollering place is actually underlain by bedrock. So the area that's shown in orange here is the surface of the bedrock, and anything below that surface will need to be dredged away as bedrock. So you can see that dredging the footprint for the turning basin in Empire will turn the entire bottom of the estuary from a sand substrate to a bedrock substrate. So how does all this compare to what we've done already? 1998 was the most recent navigation channel expansion. We went from 35 to 37 feet for 15 miles of the navigation channel, clear on up to east side to the Georgia Pacific terminal. That cost $12 million and had 90,000 cubic yards of rock. By comparison, what's proposed here is less mileage, because we're only dredging 8 miles, but there's going to be 24 times more material than that last expansion. It, again, will double the cross-sectional area, as I showed. There will be 70 times more bedrock to be removed than in 1998, and it will be 46 times more expensive. When you remove that much material from the estuary, it will increase the volume, the overall volume of the estuary. And that means that the tides in the river will take longer to flush material out of the estuary, pollution or water particles. This is some modeling work that was done. The red areas show an increase in the amount of time that water would spend in the estuary, and it would be as much as 2 additional days of time, particularly in that upper portion of the bay where our shellfish beds are. One slide for biology. This is the container terminal, a study done in 1989 for a navigation channel project then. The central column shows how many different kinds of animals lived in the sediment, and it shows how many were found in each square meter of sediment. So it turns out that section of the bay back in 1989 was a really important thing for marine animals that lived in the bottom. Certainly when we change that bottom under that footprint in that portion of the bay from sand to bedrock, it will change the kinds of animals and the types of the number of animals that live there. Finally, a number of people have shown a great deal of interest in eelgrass because it's very important for a variety of reasons. And I will just say that eelgrass lines the channel. Green showing here is eelgrass in this map. And the dredging and filling for the terminal, as well as the dredging along the margins of the channel, will decrease the amount of eelgrass. So that's it for me. In short, 3,500 pages in 15 minutes. Thanks for your attention. We'll turn it over to Christine.